So last Tuesday we have shown the John's equation. Actually, this is an eigenvalue problem, right? Has a physically meaningful solution. Means that when at the two endpoints at w equal to -1 or w equal to 1, that the solution has finite value. Okay, if and only if the parameter number is equal to n times n plus 1 for any n which is non-negative integer. Okay, and we also show the solution actually is equal to Pn. Pn is the Legendre function of degree n, or polynomial. I'm sorry, I have to say polynomial. Sorry. Okay, a polynomial. Okay, Legendre polynomial of degree n. Okay, so that we have Hn phi, right, is equal to P and cosine phi. Okay. The solution for the ODE in 12.11.5. Okay, so we first solve. Okay, and corresponding to lambda equal to n times n plus 1. Okay, so next we have to solve now the Euler-Cauchy equation in 12.11.6. That is r squared d to g dr squared plus 2r dg dr minus n plus 1 g equal to 0. Okay. Yes. Okay. So the Cauchy, the Euler-Cauchy equation has two linearly or linearly independent solutions. So that is Gn r equal to Rn, and Gn star r equal to 1 over R plus 1. Okay. Because when we studied the ODE and when we encountered the Euler-Cauchy equations, we know that the solution should be power of R. Okay, it's the power of R, and so so you can try. Actually, we are trying solutions. So we set G, we let as a power, we have okay, so we have a minus 1 plus 2a minus n plus 1 equal to 0 to solve. Okay? Because when we try this kind of solution into the Euler-Cauchy equation, okay, we will find that because here we have a minus 1 and or a minus 2, okay, from here. And so here we have a or a minus 1. Okay? So when you multiply out equal to here, you multiply this one to here, and this one is equal to RA, right? So you cancel R to the S power, okay? And then you have A times a minus 1 plus 2a minus this one. Okay, and so you have a root n and root minus 1. Right? So that is the idea. We solve the ODE, right? This is the idea. So we know a can be n or a can be minus n plus 1. And from the general theory of ODE, we know for this linear ODE and its second order, so we have at the most 2 linearly independent solutions. Okay, and we've already find 2, right? Already find 2, so that is what we want. So we are pretty lucky, right? Because this is a very simple ODE. All right, so we have that. Okay, so now we have eigen functions. So we have u and or phi, which is equal to an n en cosine phi, and un star phi equal to pn times 1 over r n plus 1 pn cosine phi for n equal corresponding to eigenvalue, and the n, which is equal to n plus 1 for n from 0 to infinity. Okay. All right, so now for interior problem. So, for example, potential, okay, within the sphere, okay. So, for potential problem within the sphere, the r, little r is from 0 to capital R. So we cannot use this kind of eigenfunctions. So we have r phi so we try. Okay. For So we consider the superposition. Consider a superposition of UN phi. Okay, so we consider such a superposition. And the boundary condition the explicit boundary condition gives us Utruta. I have to put Utruta. R phi. Okay. So summation and from 0 to infinity an en cosine phi equal to F phi. Okay, so that is so we have that. And so this is corresponding to n equal to 0 to infinity an in Bn w equals to F tilde W. Okay? Because we do the coordinate transformation. Okay? We do a coordinate transformation where F is equal to F y W. Okay? Because remember we have called, so this is the W, right? So W is cosine phi. So we have one-to-one correspondence. So this is the definition to here. And look at this one. Well, this is just the Fourier, the lambda series representation of F tilde. Okay, we encountered in chapter 11, section 5. Okay, because we use this is the Legendre polynomial, okay, and they form eigensystem. Okay, so this is one, and from that, so that we have, so we know how to find the coefficients of this series expansion. So a and r, and actually is equal to 2n plus 1 divided by 2. Let's go down. Bn plus b. Okay, so this is our formula to find the coefficients. Remember that? This is the formula of that. Okay, and now we make change to a variable. So again, we know F phi is equal to f tilde w phi. Okay? So when we make a change of variable, phi w minus sine phi d phi. Okay? So we have this is 2n plus 1 divided by 2, and phi, so phi is from 0 to pi. Okay, sorry, from 0 to pi, I'm sorry. Okay, so this correct error here. So from 0 to pi, and this is f phi, okay, pn, the sine phi, and the sine phi d phi. Okay. The minus sign is because we reverse the order. Because minus 1, alright, I have to say minus 1 is pi into 0, and this is minus sine phi d phi by the substitution here. Okay? And we reverse the order from 0 to pi, so we have phi dn phi. Okay? Alright, so for interior problem, we know how to find an, so that an is equal to 2n plus 1 divided by 2 n's power 0 to pi f phi. This is the boundary value, the value at the sphere Pn cosine phi sin phi and d phi. Alright, so an is that. And with this an brought back to here, now we find a solution. Okay? At least the formal solution, right? Satisfy the boundary condition, the express boundary condition at the sphere. Okay? The implicit boundary condition has been used because that used here. The choice of this one is because that for the implicit boundary condition at r equal to 0, we should have a finite solution, right? To have a finite solution, that we cannot use the u to the star. We have to use this one. So this is the situation. Any questions? Okay, if there's no question, so now we go to the exterior problem. For example, if you want to know the potential outside the sphere, okay, and so we consider the superposition, okay, or okay, the reason here is by the implicit boundary condition at r equal to 0. And here, consider superposition. This is because phi the implicit boundary condition at R is infinity. Yeah? So we consider the superposition of U star and R phi. So U with our U summation and the Bn. And here R to the m plus x power Bn cosine phi. Right? So we consider this one. And you know as R goes infinity, this is finished. So go to 0 as we wish, right? As we specified in the implicit boundary condition before. Okay. So we have that. And then once again, so Bn becomes to n plus 1. So that you choose R phi summation and equals 0 to infinity, and the Bn is R n plus 1. Bn phi is equal to F phi. Okay? And so again, we have summation Bn omega W F tilde W. Okay, we have that. Okay, and so as the derivation above, so finally we have 2n plus 1 divided by 2 times R n plus 1 power 0 to pi F phi Bn cosine phi sin phi d phi. So this is the solution for the exterior problem. Okay. So any questions? All right, so if no questions, I would like to introduce the method of Laplace transform. All right, I think the idea actually quite similar to the procedure we use Fourier transform to solve PDE or use Fourier sine transform to solve PDE. Okay. Alright, and so we have to know when, because we learned the one-sided Laplace transform before, right? So suppose we know how to do the one-sided Laplace transform. And the problem is, so when one of the independent, so when should we use the one-sided Laplace transform? When one of the independent variables, okay, range over the positive axis from 0 to infinity. Right? In this case, then Laplace transform, right, can be used for solving PDE. Let me illustrate the idea by an example. Okay. Right, so consider the work equation. Okay, so we consider the work equation. One dimensional, sorry. Specify. So consider one-dimensional equation. C square is the tension divided by the density, the mass density for all x greater than 0 and b greater than 0. Okay, so the work equation describing the wave traveling along the positive x-axis from 0 to infinity. Okay, so x is greater than equal to 0, and time, of course, time is started from 0. So we have such a wave equation. Such a wave equation, and with two boundary conditions. All right, so we have two boundaries. One is at x equal to 0, at x equal to 0. Okay, and we give a driving force. Okay, so we give the displacement. All right, so we actually we exert some force to move the end. Okay, by hand. Right. So here is the boundary condition. Okay. Okay. And suppose that the FP is quite simple. We give a sine wave, but for one period, so such that you have up, down, 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 back. Okay, so it's just like we give some stimulus. Okay, we give us the initial time period from 0 to pi, so that the displacement will come through, or we're going through a sine wave, okay? And then 0, okay, and then 0 otherwise. Okay, so this is at the x. So for x equal to 0, and for x equal to infinity, okay, we assume that is equal to 0, okay, for all t. This is because that I think this is physically meaningful, because the excitation is just lasts a very short time period, and then the wave will propagate. All right, and because this string has infinite length, so it takes the wave infinitely many times to travel through the string, go to infinity. So essentially, at any finite time, that as x goes to infinity, the displacement should be 0. Okay, so this is physically meaningful. So we have two boundary conditions and two initial conditions. Alright, so the initial condition is that initially, okay, the string is at rest. Okay, so this is 0. And the initial velocity is also 0. Okay. Right. Any questions about the boundary conditions and initial conditions? No? Good. All right. So now, taking the Laplace transform, all right, of the PDE, okay, with respect to what? The time t. Okay. So we have the Laplace transform equal to C squared, the Laplace transform. Okay, so we take the Laplace transform with respect to t. Okay, so this one, and we know from the Laplace transform, this is one-sided Laplace transform because the t, right, is in bracket, it's greater than equal to 0, so it's one-sided. And we know this Laplace transform is equal to S in the S domain, e minus x is 0 minus okay. So this is the Laplace transform of differentiation. And remember, when we do the Laplace transform, we fix x as parameter. Okay, so x is always fixed, and this is the initial conditions. Okay, for that. Okay, and as we know, the initial condition gives us that we have 0 displacement and the 0 velocity. All right, we have 0 initial displacement and 0 initial velocity. All right, so we have the S squared. Right, so this is the place we use the two initial conditions here. Okay, so this is here. Okay. Two initial conditions. Okay, and we let capital W x to be the Laplace transform of W. Okay, and we know this is equal to, because we are considering one-sided Laplace transform. Okay, so from 0 to infinity. Okay. As we know, in sigma system, you may learn about two-sided Laplace transform. Okay, and so, but here I just consider, because for ODE, we always assume the time parameter start at 0. We will set initial conditions. So that's why in considering the solution of ODE, usually we consider one-sided process. Okay, so this we have that. This one, the capital W, okay, is the transformed function of little w, and which exists, as we know, exists for all x greater than k by assuming that our wave is less than exponential. So it's the most exponential growth. Okay. Okay. So the displacement is assumed that it can be upper bounded by an exponential function of time. Okay. So this is pretty good, pretty big, right? So most of, I think in this problem we know this bigger problem must be satisfied, especially, I think this is enough for k equal to 0, but in general, we can always find a big enough S such that the Laplace transform exists. And here, we are talking about x to be real. In general, we can talk about x to be complex, but for the solution of ODE, it is enough to consider the S parameter to be real. Okay? So that we don't need to use the complex analysis up to now. We haven't introduced that subject. Okay, so now okay, let me complete for some constant and the k. Okay. Right. So now we have to deal with the right-hand side. Okay, the right-hand side. Now the right-hand side. Right? So this is and here we assume the order of and it's exchangeable. Okay, so we assume that. Okay, so we have okay, so the right hand side becomes to the second partial derivative of the transformed function, capital W. Okay? And we assume the order of integration and second partial derivative, partial differentiation is exchangeable. Okay, so we change that. Now we have turned the one-dimensional verification to here. C square. Which is an ODE by regarding x as a fixed parameter. Alright, so we fix x as parameter. No. We got x, alright, sorry, as a fixed parameter. The x parameter is fixed. Okay, so it's an ODE, okay, and it's a second order ODE, and we know how to solve it because this is positive, right? X is always positive because when here we assume x is sufficient big, bigger than k. Okay, and a general solution x. Okay, so a general solution is here. A S E S C x plus B x E minus x divided by Cx. And the two coefficients depends on the parameters. So we put x here, okay? Okay, to speed up. And now we have used two initial conditions here, right? But haven't used the boundary condition. So here is the place we have to use the boundary condition. Okay, so the two boundary condition give us 0 x, okay, at x equal to 0. We have t 0t. Okay, this is the boundary condition, and this is f of t. The f of t here, our boundary conditions. Okay, and we say that this is f of x. Okay, this is f of x. So f of x is the Laplace transform of this function. This function is function defined for all t greater than or equal to 0. Okay, so we have that. And at x equal to infinity, we have okay. Right. So we assume exchangeable for the limiting process and the integration. So once again, the order of is exchangeable. Okay, and we know this is 0. So this is 0 for all x. Okay? Great, then. Okay. So this is our boundary conditions. Okay? So for when x goes to infinity, this is going to be 0. Okay? Now, and the order is exchangeable. It is because I think I can for sure that let me just write down here. This is by the dominated convergence theorem. Okay, since wxt e minus xt is less than equal to m e minus s minus k t. And because x greater than k, so you have exponential decay. Okay? Because here we assume x is greater than k, so the integrand actually is upper bounded by an exponential decay function. So that's why we can exchange the integration and the moving process. Okay, and so this implies that a of x should be equal to 0 for all x greater than k. Okay, so this implies that because as x goes to infinity, this vanishes, right? And we have that. Okay, we have that, and so this is go to exponential up. So if this is non-zero, then you can't have a vanishing capital W as s goes to infinity. Okay, so only if a of x is 0. Okay. So this implies that it is 0. Okay, and so this is 0, right? But by 0x equal to ff, okay, we have, okay, but here, so we have that, but this is equal to b of x. Alright, and e minus x becomes 0. Okay, when x equals to 0, we have that p of x is equal to f of x. Okay, so the solution of our system is wx x equal to b equal to f of x and e minus x divided by c x for all and for all x greater than k. Alright, so this is our solution. And the solution, even though it's not our original form, it's a transformed solution. But we know everything because that this is from our data. Okay, from here. Okay, right, and C is our speed. So we have that. So the next thing is that okay, and so by taking the inverse Laplace transform, we have, okay, wxt, the inverse Laplace transform, okay, so we have f of x e minus x divided by c x. Okay, and by using a property of Laplace transform, because if you have an exponential function of x, you know the Laplace transform is just what? Just a time translation. Okay, so you have the f t minus x c. Okay, and unit step function t minus x c. So u is the U is the so where U is ut is the unit step function. Means that ut is equal to 1 for t greater than 0, but 0 for t is 0. Okay, so you have a unit step function. Okay, because this is a very important property of Laplace transform. Okay, so when you just time shift. So that's the solution of the one dimension of equation with the two boundary condition and the two initial condition is that x of u of xp equal to sine p minus x divided by c and 0, and this is when t is in between of here or the maximum at the initial t minus 2 pi c tc. Okay, so you can find a non-zero value displacement only at either t is in between here, okay, or x is in between here, because the wave is traveling. The wave is traveling. So you have these two, right? Because of the unit step function here. Okay, so this is just a direct, right? If you just put the sign, because this is sign transformation, and here is t is in between 0 and 2 pi. That means that t minus x over c is from 0 to 2 pi, right? So this is from here, okay? Because the duration. So this one translates to this one. But how come we have that? Because of the unit step function. Okay? Because of the unit step function here. So this gives us this one, and this one gives us this. Okay? So when you plot the time and the space diagram, you will see the behavior, the phenomenon, the wave propagation, okay, through the string. Okay. All right. I think I have to stop here. Okay. So, you have questions? I recommend you to write to have the so this is x, this is time. Okay, to see the behavior. So as time goes on, you can see the wave. Okay, how the wave goes. Okay, plot the space-time diagram to know what happened of this. Okay, if you know how to use the plotting function of MATLAB can plot three-dimensional figure for you, and that would be very clear. Okay, because we just put into this function and it will draw a three-dimensional picture for you. Okay, so that is here you have u xp, and you can see how the wave propagates. It is very nice looking figure. Okay, so anyway, I think we should have some break time. Okay, because I used the extra 10 minutes for the definition, and so and the next Thursday we will have second meeting. Okay, next is December 7th. Okay. And next Tuesday, we will have quiz number 10. As you